All right, hi everyone. We're continuing our discussion of the hydrogen atom. In the previous video, I gave you this formula for the hydrogen atom energies. And one of the important historical uses of this was that it finally gave us a firm physics foundation for the Rydberg formula. The Rydberg formula essentially has this form, and it's used to explain the line spectra of hydrogen. And I want to talk about that a little bit more in this video. If you were to ever see an energy level diagram for hydrogen or really any atom in which you are showing the transitions which produce these lines in the spectrum, you'll often see them drawn as diagonals. So the question is, why do we do that? Why do we draw the lines diagonally? And here's the answer. It's an example of a selection rule. So a selection rule is a rule that prohibits certain types of transitions from occurring. In hydrogen, the selection rule you need to be aware of is that delta L must be plus or minus 1, and delta M has to be 0 or plus or minus 1. So I can transition from an S to a P, from a P to a D, from a P to an S, but I cannot transition from an S to an S, or a P to a P, or an S to a D, because those break the selection rule. Now the next question is, well, where did the selection rules come from? And I want to give you two arguments. The first is a mathematical one. It turns out that the spherical harmonics follow a set of recursion relationships like the harmonic oscillators. And if you frame the absorption of a photon, you end up with an expression which looks like this. Right? This specific form applies directly to the recursion relationships for spherical harmonics. And those recursion relationships will require that this integral will equal 0 unless these conditions are true. So one argument is simply that the selection rules fall naturally from the mathematical relationships that result from the spherical harmonics. Now, that's all well and good, but no one's ever convinced by mathematical arguments. Right? You want something more than that. And so I want to give you a different type of argument, which is a physical argument based on the conservation of momentum. And in order to do that, I need to take sort of two side steps. The first side step is to talk about spin. So this is in Atkins 8b. It's going to be extremely important in the context of multi-electron atoms where we're headed. What I need to tell you is that electrons contain spin, which is an intrinsic property like charge or mass, and it manifests itself like an angular momentum. So you can imagine that an electron is spinning around its own axis. It is precessing. So it's both whipping around the nucleus and spinning. Now, if you were to look at Atkins' full description of spin, this is what he says. A detailed analysis of spin shows it is sophisticated and shows that the property should not be taken to be an actual spinning motion. However, the picture of the spinning motion can be very useful when used with care. I'll also post a link to a discussion from Albert Fair, who won a Nobel Prize for his work with spintronics, about what spin is. I often say that spin is something which walks like a duck, looks like a duck, and it quacks like a duck, but it's not a duck. Okay. So it's spinning. We can basically think of it in that way. And because it's spinning, there's an angular momentum associated with it. Here's what you need to know. Just as the orbital angular momentum, the motion around the nucleus, is described by the quantum numbers L and M, spin is described by quantum number S and M sub S. S is the spin angular momentum, N sub S is the Z component of spin angular momentum. It turns out that there is one spin for an electron. There's only one possible spin, and that is 1/2. If S is equal to 1/2, it's the only possible value, then the projections are S, S minus 1, dot, 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 to minus S. In other words, it could be 1/2 or negative 1/2. It can be spin up or spin down. It can be spinning clockwise or counterclockwise. Those are my two options. I think you know all of this, and I'm going to leave it at that. We will simply add spin in an ad hoc manner moving forward. Right? However, you should be aware that this arises naturally when you combine the Schrodinger equation with Einstein's special relativity. Right? So it arises naturally when you combine quantum mechanics with special relativity. That's the first thing I need to tell you. The second thing I need to tell you is about the standard model of particle physics. So the standard model describes elementary particles and the interactions between them. Interactions are sometimes called quasi-particles. So it's represented in this chart here, right? And you'll see some names of things that you might recognize. For instance, like neutrinos, muons, there are electrons, photons, gluons, weak forces. There are all these quarks, up, down, left, right, charm, whatever they are. I always swear that the physicists were smoking something really good when they came up with the names for the quarks. If you look at this type of chart, you'll notice that there's a couple pieces of information. So in addition to the name, there's a mass. Okay, note this is given in energy units. There's a charge, and there's a spin. And what I need to point out to you is that these spins come in one of two flavors. The first are particles, which have spin 1/2. So basically everything over here is a spin 1/2 particle. And we refer to those as fermions. The other flavor are the things over here, which all have integer spins. They're spin 1 systems. We refer to these as bosons. Now, next step is that everything over here, which is a spin 1/2, a fermion, is something that makes up matter. Right? So electrons, right, those have mass. Quarks make up the parts of a nucleus. These all generate matter. The bosons, the integer spin particles, constitute the forces that bind things together. So a photon is an electromagnetic force. The weak force has to do with radioactivity. Right? Gluon has to do with the strong force, holding the positive protons together in the nucleus. So photons spin 1, electrons spin 1/2. Those are the two things I need to tell you. Let me go back to my original question, which is, why is delta L equal to plus or minus 1? Well, the question is, does photon have angular momentum? And the answer is absolutely not, right? It does not. However, it does have spin, right? And what is spin? Well, it's something which acts like an angular momentum. It walks like a duck, it quacks like a duck, but it's not a duck. How much spin does a photon have? Well, it has 1 quanta. Right? It's an integer spin, a boson. And if an electron absorbs a photon with 1 quanta of angular momenta, then its angular momentum has to change by 1 quanta. Angular momentum is conserved. Right? What quantity describes the angular momentum of an electron? Well, it's L. Right? And therefore, delta L must be plus or minus 1. You have to change by 1 quanta. Right? Sorry. That's where this selection rule comes from. I hope you like that a little bit better than the math. And will be useful to keep in mind moving forward. See you next time.